All right, so, because I'm an idiot, I forgot to restart the recording. So I'm going to try to walk you through the solution to this. Unfortunately, I kind of have the answers already on the board, so it's not quite the same. So the first thing you need to do to solve any of these is to construct the cycle in the phase diagram. And there are two graphs that we usually use. The first one we've done a lot of, which is PV. The area inside would give the work. Another graph is TS, which is very similar to TV. It's kind of similar, so sometimes when I talk through it, I'm going to use that as a basic, kind of to make an analogy with the TV diagram we already saw. As I said, this is the area of the PV diagram gives you the work, and that came because the definition of work, let me use blue so it's more visible. The definition of work was the integral of P dV. So that integral would compute an area inside that phase diagram. Similarly, we saw that a little bit of heat was equal to TdS, which means that if you integrate that around the cycle, that the heat of the cycle is the integral of Tds. So this is a nice diagram. Temperature versus entropy is nice because the area inside that gives you the heat. So the area inside P versus V gives you the work. The area inside temperature versus entropy gives you the heat. It's a little harder to conceptualize because entropy is just a more complicated concept, but mathematically it works very analogously. Now, let's go through what we know. So the basic assumptions we have are going to be, let me stick here. The basic assumptions are going to be that we're using ideal components, which means that the turbines and pumps are isentropic. The entropy is constant. That means that there's no heat transfer rate and also that they're reversible. And then we're also going to assume that the boiler and condenser are isobaric, the constant pressure. Okay, so they're kind of working through this. I'm going to kind of dance between these two graphs and kind of talk my way through it to give you an idea for what's going to happen, and then we'll get numbers out. But you can't really get through it until you know what's going on. I can't remember in the last video if I numbered the states this way. So I'm going to label the states after. So I've got a boiler, a high pressure turbine, back to the boiler, to a low pressure turbine, through the condenser, through the pump, and back to the boiler. Those are the components of a reheat Rankine cycle. And I'm going to label the states 1 through 6, starting with after the condenser. So after the condenser is state 1, after the pump is state 2, after the boiler the first time is state 3, after the high pressure turbine is state 4, after the boiler the second time is state 5, and after the low pressure turbine is state 6. So those are my states. Okay? So now let's go through this. The problem, we knew a lot about what happened after it left the boiler the first time. We knew that that's the highest pressure, high temperature and high pressure configuration. So, right. So that was state 3, high temperature, high pressure configuration. So, and we know it's going to be steam, right? You boil it, right? So it's steam. So we know that that's definitely way over here in the vapor state. Okay, so high pressure and high temperature. Now I can work backwards to get to state 2, because at state 2, which is before the boiler, I know that that's right after it leaves the pump. And if you're leaving the pump, it must be a liquid state. And I also know that the boiler is constant pressure, which means that when I work backwards, so state 3 is a gas, state 2 must be a liquid at the same pressure. So that's just a horizontal line in this diagram. And then I think to myself, well, what does that mean about a temperature versus entropy? And again, I'm going to use our intuition. Roughly, for purposes of sketching, constant pressure curves at least, it's very similar to an isobar on a TV diagram. So what we're going to have here is before the boiler, well, the temperature would be lower, and I know so the temperature is going to go down, plateaus when it's in the middle of the phase transition, and then when I get to the liquid side, it's going to go down some amount. So I just put it there. Okay, so it's in the liquid state, and it's at lower temperature, and I'm not putting numbers on this, so that's good enough. I think usually people would actually draw it much closer to the temperature at state 1, but all right, I'm just gonna put it there. So in the state 2 in a PV diagram is along a horizontal line relative to state 3, and on a TS diagram, it's going to be at a lower temperature, and it's got this zigzag because the boiler is constant pressure, and inside the mixed state, constant pressure means constant temperature. Okay, great. Now, okay. One other thing we know is that, okay, so now from 3 to 4, if we think about our cycle, from 3 to 4, that's going through the high pressure turbine. So you've got you're pulling work out, so you're drawing energy out. That's going to cause the temperature and pressure to drop. So, how are you going to do that? Well, so from 3 to 4, the temperature and pressure should drop. Probably the easiest way to figure out what's going on from 3 to 4 is to look at the temperature entropy diagram, because through the turbine we know that the entropy is constant. So from 3 to 4, it's going to be along a vertical line straight down, because the entropy has to remain constant. Put my arrows on there, I forgot to. Okay, so from 3 to 4 through the first high pressure turbine, it goes straight down. On this curve, I think I didn't really draw it very well even. On this curve in a PV diagram, remember we're over here in the gas state from 3 to 4, and there's no heat. So if you remember from our discussion of an ideal gas, we expect that to kind of kick out a little bit. So the pressure drops, it has to go down across the turbine, and it actually goes out a little bit, so for an adiabat, which means no heat. So state 4 is here. So on this graph, 3 to 4 is on a diagonal. I got a little curvature really. And over here it's a vertical line because it was isentropic. And then from 4 to 5 is the reheat back through the boiler the second time. So it's isobaric. So state 5 is connected to state 4 by an isobar. And then the problem told us that after it left the boiler, we assumed it boiled long enough to reach that 600 degrees Celsius number that we had at state 3. So the problem told us that the temperature at state 5 is back up where the temperature at state 3 was. So the pressure is lower than state 3, but the temperature is back up at the same. So on a PV diagram, from 4 to 5 is a horizontal line. On a TS diagram, it's back up at the same temperature. After state 5, it goes through the low pressure turbine. Again, a turbine is assumed to be an ice-intropic device. So that means the entropy is going to be dropping straight down, and the problem tells us that the quality at state 6 is 0.896, I think is the number, just off the top of my head. So we know it goes all the way down into the saturated state. So I know that happens. And here, well, again, it's a gas. It's going to go out. It's going to kick outwards a little bit. So it's going to end up but it has to be inside the saturation curve here, because the quality is given at state 6. Okay? And then from 6 back to 1, we're going to take it to be saturated liquid. What you really could do is, well, we're just going to take it to be saturated liquid. That's what the example in the book did. And so even though they didn't spell it out in their assumptions, that's what we're going to assume. So we're going to take state 1 to be saturated liquid, so it's all the way on the left hand of the saturation curve. And from 6 to 1, that was through the condenser, so that's constant pressure. So that's a horizontal line, but if the pressure is constant, the temperature is constant. So there you go. Going back finally from 1 to 2, that's in the process of going through the pump. When you go through a pump, it's a liquid, so you can't change the volume very much because it's not compressible. So basically, it's going to pretty much be a vertical line on this graph. It might have a little slope, it might have a little bit of an angle, but basically, it's a vertical line, and we have to end up wherever we were at state 2, which was at the same pressure as state 3. Over here, to get from 1 to 2, you should keep the entropy constant because the pump is assumed to be ice-intropic. So, we've got our phase diagram, and then I'm going to list all of our different assumptions now. So, what we can assume, if I got enough room here, hopefully this is visible, we can assume that pressure at 3 equals pressure at 2. We can assume that entropy at 3 equals entropy at 4. We can assume pressure at 4 is the same as pressure at 5. Then we can assume that entropy at 5 is the same as entropy at 6. We can assume pressure at 6 is the same as pressure at 1. And we can assume entropy at 1 is the same as entropy at 2. So we have all these things that are related to each other. And these are the kind of keys to working out the algebra. I hope that's all visible. Let me tilt. I'm sorry. Angle's not very good. So I'm just going through wherever there's a horizontal line, that tells me that the pressures are the same. Wherever I have a vertical line, that tells me that the entropies are the same. Furthermore, I know that the temperature at 5 equals the temperature at 3, which was 600 degrees Celsius. Furthermore, I know the pressure at 3 was given as 15 megapascal, which is also 150 bar. and I know that the pressure at state 6 and state 1 equals 10 kilopascal. And I know the quality at 6 is 0.896 and the quality at 1 is 0 because I'm going to assume it's saturated liquid. So these are the kind of numerical assumptions I'm going to make. These are the algebraic assumptions I'm going to make just caused by assuming ideal devices, ideal turbines and ideal boilers and pumps and things. And the rest of it is just a fun slog. And I'll tell you, it took a while in class to work through it. I wish I had recorded the whole thing. I'll tell you how I did it. You should pause it and try to work through the numbers. On the test, kind of as I said before, within reason, you should make reasonable assumptions and cheat when you need to. You know what I mean? Not really cheat, but on a big problem like this, if you really interpolate everything every possible time, it takes forever to do it by hand. I would say on the test, unless the problem says explicitly interpolate where needed, if it's near points on the table, then just use that fact. Okay, so let's go through what I would do. Now, I still have here written the order that I suggested that people work it out. You could do it differently. But in all cases, whenever you have one of these cycles, you should start with the states where you know the most and then work from there. So in this cycle, we know the most about state 3 because I know a pressure and a temperature. We know everything about state 6 and state 1 because we know their pressure and we know their quality. So we know we can get everything there. So I would start with so 3, 6, and 1 are the ones where you could, just from the beginning, work everything out. Okay? Now, the goal is to calculate, ultimately, you're trying to find efficiencies, but that means you need to find heats and works or powers and heat transfer rates, Q dot and W dot. To do that, you're going to need to find enthalpies. So for every state, you have to, in one of these cycles, you have to find all the enthalpies. That's for sure. So if you have, in this case, we have 6 states, you have to find 6 enthalpies. On top of that, you may need to find other numbers so that you can kind of map your way around the tables. Okay. So, and again, you need 2 numbers for each state. So at state 1, over here, I suggested starting with state 3 because that was one of the states where we knew a lot. So at state 3, we know a temperature and a pressure, 600 degrees Celsius and 150 bar. Well, okay, so you look in the tables, and I don't think that one's quite in there, but you can kind of estimate. What I would do is, first off, find the enthalpy, and I don't know if you can read this, I hope so. 3582 kilojoules. So that was our estimate or interpolation. I can't remember which one. I can't remember if we actually interpolated that one or that's just the estimate. But so basically 3580 plus some rounding in there. And okay, so that's state 3. And then if I look over here, I go over here, for state 4, I'm going to figure out that I'm going to need to use the entropy to identify state 4, which means I need to, and I know that that is equal to the entropy of state 3. So while you're dealing with state 3, you should go ahead and look up the entropy of state 3. By itself, it's not such an interesting number, but we need it to identify what's going on at state 4. Okay? Okay, so that will take care of state 4. Now let's talk about state 6. So I should say this. That would give us the entropy at state 4, but But I don't know anything else yet about state 4. I think one of the questions was to find the pressure at state 4. That would be the pressure going into the, that would be the pressure the second time through the boiler. So right now, after you find the entropy at state 3, you need to find we want to find the pressure at state 4, but I don't know how to do that yet. So we have to find some other number. And then we go to state 5. And at state 5, we know a temperature, but we don't know pressure about that either. Okay? So we push it back one more level. Let's go to state 6. At state 6, we know the quality and we know the pressure. We know it's at 10 kilopascal, and we know the quality is 0.896. So what we can do at state 6 is look up the enthalpy, because we're always doing that. And then while we're there, go ahead and calculate using quality, for both of these actually. Use quality to find the entropy at state 6. So use the quality twice, once to find the enthalpy, once to find the entropy. And then because one of our relationships is the entropy at 6 is the same as the entropy at 5. Okay? So once we know the entropy at 6, that tells us the entropy at 5. And we already knew the temperature at 5 was 600 degrees Celsius. So if you know the entropy at 5 and the temperature at 5, that's two numbers. You can use those to find the enthalpy at 5 and also the pressure at 5. So the logic is you find the entropy at 6, which gives you the entropy at 5. Since you already were given the temperature at 5, that's two numbers. You can find anything you want in principle. So you want to look up the enthalpy and pressure at 5. And since from 4 to 5 is through the boiler the second time, implicitly that's the pressure, or not implicitly, but that's going to give you the pressure at 4. So in which case, if you're keeping track of all this, if you go through all this, we will know the entropy at 4, because that's the same as the entropy at 3. And if you work backwards, now we know the pressure at 4. You can use those two numbers to calculate the enthalpy at 4. I know it's a lot of find this, find that. I'm going to go through the map of all this. You should pause it, kind of work through the logic again without using numbers. Just logic, why I'm saying to find what I'm saying to find, and then continue on. You can see how the numbers work out. Okay. So at this point, we would have H3, H6, H5, H4. We're almost done because there's 6 states, and we would have the enthalpies for 4 of them. State 1 is easy because that we assumed had quality 0. So that one we could have actually found straight off at the beginning. That you just use quality, it's just saturated liquid. So you can just read off because you know the pressure at state 1 is 10 kilopascal. So you know the pressure at state 1, you know it's saturated liquid. You immediately just look up the enthalpy and entropy. And then the last thing we're going to do is figure out the enthalpy at state 2. And at which point you have all of the enthalpies of all the states. Even though we have to use entropy and pressure and temperature and all that other stuff, what we really care about are the enthalpies. Those other numbers are just kind of the numbers we need to work our way through the tables. Okay, so that's kind of the plan. I'm going to kind of summarize how we got that. Mostly, we just estimated things to get numbers. So, okay. So if you've got that logic, then let's go through this. As I said before, using the temperature and pressure for state 3, we can find an entropy, S, which was 6.6786, and an enthalpy, which is 3582. Sorry for using green. Let's see if I can bring this a little closer. That's better. I don't want my computer to fall, but maybe it'd be a little bit better to read, maybe. Okay? Focuses on me, maybe it'll focus on this. All right, so those are my numbers for state 3. And then for state, the next number I was going to find was, next state I was going to deal with was state 6. So I used the quality at state 6 and the pressure at state 6. And then using that, you can calculate an entropy of 7.37 kilojoules per kilogram Kelvin. Entropy should be kilogram Kelvin. And an enthalpy of 2335.8 kilojoules per kilogram. Okay? Now, so that gets you to state 6. We know everything. Working backwards to state 5, we know that the entropy of 5 is the same as the entropy of 6, and we know the temperature of 5 is the same as the temperature of 3. Sorry, I got to zoom back out again. Sorry. The temperature, so for state 5, we know that the entropy of 5 is the same as the entropy of 6. We know the temperature of 5 is the same as the temperature of 3, namely 600 degrees Celsius. Looking at your tables, it's not exactly one, but it's really close to 600 degrees Celsius and a pressure of 40 bar. It's really close, looking at the entropy numbers. And so it's certainly within the limits of the accuracy of our calculation. You can just take it to be 40 bar, which is the answer to the question A. What's the pressure going into the reheat boiler? 40 bar. And that matched what the other book that I got this problem from used, and they had different tables than us, but you know, their tables had different information, but it all matched within the rounding. And then once you know that it's at 40 bar and the temperature 600 degrees Celsius, you can just read off the enthalpy, and we found, 3674.4 kilojoules per kilogram. I don't know what sorry. Kilojoules per kilogram. Okay, so that gets us the enthalpy at 5. And we know the pressure at 5 is 40 bar. But the pressure at 5 is the same as the pressure at state 4. So state 4 has a pressure of 40 bar. On the other hand, we know the entropy at 4 is the same as the entropy at 3. That's one of our assumptions here. Entropy at 3 and 4 are the same. So at state 4, we now know the entropy and the pressure is 40 bar. You look at the tables, and I put a tilde here, or a rough equals. We estimated this, and we got 3150 was our estimate. If I remember right, if you look in the table, it falls about 1/3 of the way between the different rows in the gas state, because it's in the vapor side of it, of the phase transition. And you can just estimate it that way. I think the book that actually worked it out in more detail had 3155. So 5 kilojoules is nothing in the scheme of what we're doing here. All right? And then, okay, so that gave us the enthalpy at state 4, and that would be kilojoules per kilogram. Great. So that, at this point, we know enthalpy is at 3654. Now we go to state 1. State 1 was saturated liquid at 10 kilopascal. That's just straight off the table. You immediately just read off the enthalpy at state 1, and we looked up and it was 191.83 kilojoules per kilogram. And at the same time, we need to find the entropy, which would be 0.6493 kilojoules per kilogram Kelvin. And then, okay. And now we come to state 2, the only one left. And our tables are not as accurate as the one in the other book. They give more numbers. It's in the liquid state, which is where we don't have many numbers in our book. And so you're going to have to cheat. They gave, well, so what we assumed was, well, we know the entropy, right? We know the entropy at state 2 is the same as the entropy at state 1, and we knew what else did we know? Sorry, lost my train of thought. Oh, and we know the pressure at state 2. So if you look at the tables and you look, what you can see is that it's kind of hard to just from the liquid table to estimate, and we could do a better job. But there's no point, because if you look at the enthalpies for anything with even close to a pressure of 15 megapascal or 150 bar and an entropy of 0.6493, the enthalpies are all really close to 200. Now, the other book I was looking at, they had better tables and stuff, and they actually got 205, I think. Maybe 205 or 206, something like that. But even with ours, you can just see they're all right around 200. Furthermore, look at what's happening here. When you go from state 1 to state 2, that's going through the pump. And that means that the energy change, or the enthalpy change, which is what we're going to care about, is going to be associated with the enthalpy at the difference in enthalpies. And if you use our book, you're just eyeballing it, we got about 10 kilojoules. And then using the more accurate one, they get 15 kilojoules. But again, it doesn't matter, because we're talking about 5, 10, 15 kilojoules. That's nothing when you're talking about a cycle that's got thousands of kilojoules. This, is way below our margin of error. In fact, a lot of times when you're just doing rough calculations, or even not so rough calculations, you just ignore the pump anyways when you're calculating the energy. Right? So you'll see, in fact, when we get our final answer, we estimated this in our crude way. They did a better job, but to 3 digits, we got the same efficiency because the contribution of the pump was so small, it just didn't matter. Okay. So on the test, you can cheat that way, or look at the tables and make an estimate, and it's not going to matter. The liquid states are not going to be important for these power cycles. Okay, so at this point, put my units in. At this point, we have all of the enthalpies, H3, H6, H5, H4, H1, and H2. They're all known. H4 and H2 are probably, that's where we kind of had to cheat the most. H2 is definitely the crudest one. The other ones are actually quite close. When you look at the tables, you'll see that. H2, we definitely just kind of looked at it and we were like, I don't want to do all that work. So just, because you're working hard for not much. Okay. Now, how do we pull that stuff together to get the answer, the efficiency? First off, we were supposed to find the pressure at the reheat cycle. That was that 40 bar number. So we got that one done. And then we want to find the efficiency. Remember, efficiency is the power of the cycle divided by the heat transfer rate in, or is the work of the cycle over the heat in. So let's go through. The power of the cycle would be the power at the high pressure turbine, the low pressure turbine, and the pump. The two turbines produce power, so these would be positive numbers. The pump consumes power. That'll be a negative number. But this is a power plant. It's going to produce way more than it's going to consume in its pump. So the work of the pump is going to be just a tiny number. In fact, again, I think you don't even see it in our, it's well below our margin of our percent error. So it would have worked out almost exactly the same, you just dropped it. Anyways, so it's the work power of the cycle divided by the total heat into the cycle. So I look at the heat transfer rates into the cycle. That would be the heat both times it goes through the boiler. So that's the heat between states 2 and 3 and 4 and 5. And then the way I relate the power and heats to enthalpies is using our general control volume equation, which says that the heat transfer rate minus the power equals the mass flow rate times the enthalpy at the exit minus the enthalpy at the inlet. And there's also kinetic and potential energy stuff, but that just doesn't matter. So just don't worry about it. And so for each one of these, high pressure turbine, low pressure turbine, the pump, the boiler the first time, the boiler the second time, I just went through and used this formula and related the powers and heats to the enthalpies. Now, you'll notice when you go through that, we know lots about the enthalpies. We don't know anything about a mass flow rate. In fact, you don't need to know it for the efficiency. If they had said find the heat transfer rate or find the power, singular, find it, you would need to know what m dot was. However, the efficiency is a ratio. And so, sorry. My screen saver went on. The heat transfer rate is a ratio, in which case this m dot would always cancel. If you wanted to, you could just pretend it's 1. Okay? So let's go through this. To find the power of the heat pump, so the power, that's W dot, has a minus sign here. There's no heat, not heat pump. The power of the high pressure turbine, that HP is high pressure. There's no heat for that. And to get W dot, you have to bring the minus sign over, which means it's going to be ingoing minus exit. In minus exit. For all of these power producing devices, it's the ingoing enthalpy minus the outgoing enthalpy. And so I look at my high pressure turbine and I see that the ingoing is state 3, the outgoing is state 4. So the high pressure power is going to be m dot times H3 minus H4. For the low pressure, it's going to be H, so that's over here, that's going to be H5 minus H6 times m dot. For the pump, it's going to be H1 minus H2. The total power would just be the sum of all these. For the heats, the devices with heat would be just the boiler here. I just realized I made a mistake when everybody else was here. Sorry. We also, I just forgot to write it here. You also have to include the heat of the condenser. So okay, I forgot that one. The heat, no, that's right. No, it's fine. It's fine. It's good. For the efficiency, you only include the heat going into the cycle. So the condenser is, you don't pay money for that. The air takes care of that, so you don't care about that for finding the efficiency. So we just include the heats for the boiler. So that's going to be the heat at 2 and 3 and between 4 and 5. The boiler has no propeller blade, nothing like that. So there's no work being done. So for the boiler, you can ignore the work and you just say the heat is going to be the heat, the enthalpy leaving minus the enthalpy coming in times m dot. So the first time through the boiler from 2 to 3, that's H3 minus H2, and then second time through the boiler is 4 to 5, that's going to be H5 minus H4. and the total heat, would be the sum of these. And then I put it all together in a one big ratio. So I just add up in the numerators the total power of the cycle. So that's going to be H3 minus H4 plus H5 minus H6 plus H1 minus H2. So I'm just adding these up. That goes in the numerator. In the denominator, I divide by the heat into the cycle, only into, in which case that would be H3 minus H2 plus H5 minus H4. So I've got all these numbers. If you don't have them written down, go back and rewatch that. Got all those numbers for the enthalpies. You put them all in. That number, that ratio, you got to type it in your calculator. That gives you the efficiency. And when it comes out to be 0.45, which is exactly what the book had. And they did a little bit more accurate job on their estimates. And they cheated a little bit less than us, but it turns out it doesn't matter. So that's how you do it. So, and then we also talked about, kind of briefly, a lot of the stuff that you and I had talked about on the test. So, kind of things to study, and we'll talk a little bit more about that on Thursday. So, all right, let's see.